I see, I see. So I also noticed a similar problem as yourself across society, so across history, that people entwine this prevalent application with some ontological status. So what I mean by that is you'll have a tool which is ubiquitous in usefulness, and then you start to think that there's some reality synonymous with that. So another example would be an ancient poet who would see the power of poetry and think that what lies at the fundament is narrative pieces, or a mystic who sees consciousness everywhere almost by definition and then believes consciousness must lie at the root of reality. And some people, Max Tegmark would be an example of this, find that math is so powerful it must be what reality is. So it's also not clear to me whether computation is another such fashionable instance of a tool being so powerful that we mistake its effectiveness with its substantiveness. And I understand that Stephen may think differently. I understand that you may think differently. So please explain.
That's a fantastic point, and I suspect, from at least from what you've said, I think our views may be quite similar on this. That I'm reminded of this meme that circulated on Twitter a little while ago about people saying, immediately after the invention of kind of writing systems and narrative structure, everyone goes, yes, the universe, the cosmos must be a book. Right. And then, immediately after the invention of mathematics, yes, the cosmos must be made of mathematics. And then it's, immediately after the invention of the computer, yes, the cosmos must be a computer. I think that, it's a folly that we've fallen into throughout all of human history. And so, my feeling about this is always that, we build models using the kind of ambient technology of our time. And when I say technology, I don't just mean, nuts and bolts technology. I also mean kind of thinking technology, right? So, there are kind of ambient ideas and processes that we have access to. And we use those as a kind of raw substrate for making models of the world. So, it's unsurprising that when people like Descartes and Newton built models of the cosmos, of the solar system and so on, they described them in terms of clockwork, by analogies to clockwork mechanisms, right? And, Descartes even sort of more or less directly wrote that he thought that, the solar system was a piece of clockwork. Whether he actually thought that in an ontological sense or whether it was just a kind of poetic metaphor, I don't completely know. But, it's sort of obvious that would happen, right? Because, the 15th century, 16th century, that was sort of the height of clockwork technology in ambient society. And so, we live right now in arguably the zenith of kind of computational technology. And so again, it's completely unsurprising that we build models of the cosmos based largely or partly on computational ideas. Yeah, I agree. I think it would be a folly. And I think you're right. This is maybe one area where perhaps Stephen and I differ slightly in our kind of philosophical conception. I personally feel like it's folly to say, therefore, the universe must be a computer, right? Or my feeling about it is the strongest we can say is that, modeling the universe as a Turing machine is a useful scientific model, and it's a useful thinking tool by which to reason through kind of various problems. I think it's, I would be uncomfortable endowing it with any greater ontological significance than that. That being said, of course, there are also lots of examples where people have made the opposite problem, right? Where, or made the opposite mistake, I mean. So, the classic example is people, say Hendrik Lorentz, right? Who basically invented the whole formalism of special relativity. But he said, oh, no, this is just a mathematical trick, right? He discovered the right form of of time dilation and length contraction, but he said, this is just some coordinate change. It doesn't have any physical effect. It's just a formalism. And then really the contribution of Einstein was to say, no, it's not just a formalism. This is an actual physical effect. And here's how we might be able to measure it. And so, I'm just trying to, I'm trying to indicate that you have to thread a delicate needle there. Yeah.
So you mentioned Turing, and there's another approach called Constructor Theory, which generalizes Turing machines, universal Turing machines, to universal constructors, so-called universal constructors. So I'd like you to explain what those are to the degree that you have studied it, and then its relationship to what you work on at the Wolfram's Physics Project. And by the way, string theory, loop quantum gravity, they have these succinct names, but WPP, it doesn't have a graspable, apprehensible name, at least not to me, to be able to echo that. So is there one that you all use internally to refer to it?
Okay, so on that, I agree. I'm not a fan of the naming of the Wolfram Physics Project, or indeed even the Wolfram model, which is a slightly more succinct version. in a lot of what I've written, I describe it. I use the term hypergraph dynamics, or sometimes hypergraph rewriting dynamics.
Okay.
Because I think that's a more descriptive title for what it really is. But no, I agree. I think as a branding exercise, there's still more work that needs to be done.
So for the sake of us speaking more quickly, we'll say the HD model. So in this HD model,
okay.
What is its relationship to, what was it, category? No, it wasn't category. It was
Constructor theory.
Constructor, right? Okay, so what is the HD model's relationship to constructor theory?
Although that's an interesting Freudian slip, because I think basically the relationship is category theory, right? So, yeah, okay. So I mean, with the proviso that, again, I know that you've had Chiara Marletto on TOE before, right? So I'm certainly not an expert on constructor theory. I've read some of Chiara's and David Deutsch's papers on these topics, but so yeah, as you say, I can give an explanation to the extent that I understand it.
Mm-hmm.
So, with as I understand it, the central idea with constructor theory is, rather than describing physical laws in terms of kind of equations of motion, right? So in the traditional conception of physics, we would say, you've got some initial state of a system, you have some equations of motion that describe the dynamics of how it evolves, and then it evolves down to some final state. The idea with constructor theory is, you say, rather than formulating stuff in terms of equations of motion, you formulate things in terms of what classes of transformations are and are not permitted. So, I think one of the classic examples that I think Deutsch uses in one of his early papers, and I know that Chiara has done additional work on, is the second law of thermodynamics, and indeed the first law of thermodynamics, right? So thermodynamic laws are not really expressible in terms of equations of motion, or at least not in a very direct way. They're really saying quite global statements about what classes of physical transformations are and are not possible, right? They're saying you cannot build a perpetual motion machine of the first kind or the second kind or whatever, right? That there is no valid procedure that takes you from this class of initial states to this class of final states that, reduce global entropy or that, create free energy or whatever, right? And that's a really quite different way of conceptualizing the laws of physics. So constructor theory, as I understand it, is a way of applying that to physics as a whole, to saying we formalize physical laws not in terms of initial states and equations of motion, but in terms of initial substrates, final substrates, and constructors, which are these general processes that I guess one can think of as being like generalizations of catalysts, or it's really a kind of a grand generalization of the theory of catalysis in chemistry, right? That you're describing things in terms of, this enables this process to happen, which allows this class of transformations between these, these classes of substrates or something. Now, you brought up, inadvertently, you brought up this question of category theory, or this concept of category theory. And I have to be a little bit careful with what I say here, because I know that the few people I know who work in constructor theory say that what they're doing is not really category theory. But I would argue it has some quite, in terms of the philosophical conception of it, it has some quite remarkable similarities. So, to pivot momentarily to talk about the duality between set theory and category theory as foundations for mathematics. So, since the late 19th century, early 20th century, it's been the kind of vogue to build mathematical foundations based on set theory, based on things like Zemilo-Frankel set theory or Hilbert Bernays-Gödel set theory and other things, where the idea, your fundamental object is a set, some collection of stuff, which then you can apply various operations to, and the idea is you build mathematical structures out of sets. Now, set theory is a model of mathematics that depends very heavily on internal structure, right? So, for instance, in the standard axioms of set theory, you have things like the axiom of extensionality that essentially says two sets are equivalent if they or two sets are identical if they have the same elements. Right. So it involves you saying, identifying sets based on looking inside them and seeing what's inside. But there's another way that you can think about mathematical structure, which is you say, I'm not going to allow myself to look inside this object. I'm just going to treat it as some atomic thing. And instead, I'm going to give it an identity based on how it relates to all other objects of the same type. So what transformations can to give a concrete example, right? Suppose I've got some topological space. So this kind of set theoretic view is, okay, that topological space is a set of points. It's a collection of points that have a topology defined on them. The kind of more category theoretic view would be to say, actually, that topological space is defined as the collection of continuous transformations that can be applied to it. So that space can be continuously deformed into some class of other spaces. And that class of other spaces that it can be deformed into is what identifies the space you started from. And so and you can define that without ever having to talk about points or, what was inside it or anything. In fact, there's this whole generalization of topology called pointless topology or locale theory, which is all about doing topology without an a priori notion of points. So in a way, it necessitates this conceptual shift from an internal structure view to a kind of process theoretic view. And so that was a viewpoint that was really advocated by the pioneers of category theory, Samuel Eilenberg and Saunders MacLean, and also some other people who were working in topology, like Jean-Pierre Serre and Alexandre Grothendieck and others. There was a kind of radically different way to conceptualize the foundations of mathematics.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for Toe Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.